and zeros. And this is sent to a multiplexer where many such information comes through and enters this multiplexer and makes it to and combines them and send it through an optical fiber. And this optical fiber carries to the place where this information has to be carried. And there will be a demultiplexer where this again the signals are segregated and sent to a detector. And from the detector, the ones and zeros or the packages are sent back to your the laptop that you're viewing at. So this is how the entire system works. So if you have to improve the system, the easiest way is like making more and more of this entire setup, say lay more and more optical fibers or add more and more lasers. But this have a price to give up. It's basically, like if you want to add more and more optical fibers, it costs quietly very high, and the time process that is needed to put these optical fibers or establish new data centers is too high, and it is again consuming a lot of energy, and it will be against all the norms the current world is going towards, which is like an zero emission world. So it's more like energy, it is not at all energy efficient. So all these problems are there. So we have to see an alternative, like still use a lesser energy, but able to send more information should be our ideal way to go with. So if you have to do that, the one easiest way is to make this electro-optical modulator or the device which creates its ones and zeros as fast as possible, so that you can send a lot of ones and zeros in a shorter time. Or the other way is like add more and more lasers in the line so that you can transfer more information in a shorter time. So this is the two areas one can modify a lot. So one should know that, like, if the laser, if I use much more lasers in a different frequency, then I need an amplifier that can amplify in those frequencies too. So these are the areas that one can improve. So currently, in the conventional infrastructure, these things had been taken into account, had been modified a lot. But our lab from we showed that we can integrate all these things into a single chip with our collaborators from Monash and Swinburne. We showed that we can transfer around 44 terabits per second of data from here from RMIT to Monash. So this is like a real world demonstration. And at that time, we have recorded the world's fastest internet. And when I say 44 terabytes per second, it is equivalent to the entire Netflix cloud downloaded less than a second. So think about in future, where you can download or stream much higher quality videos. This is quite possible with this current chip. And how we have achieved it is basically like, as I said earlier, we need more and more lasers. But what we have done, we integrated a technology known as frequency comms, which acts as a laser. So that is what you look over here. So it have a lot of lines like comp. So you have your hair comb, right? So if you take your hair comb, it have distinct lines of comms, right? So the same way we make a laser that can create distinct lines in different frequencies if within a single pulse. So this is how a frequency comp looks like. And this is a Nobel Prize winning technology back in 2005 for physics. So this has been integrated into this particular chip. And the other thing is like using a high-speed modulator that works in around like 40 gigahertz and more. So these are the two things we incorporated. And we have shown this demonstration. But after this demonstration, our team was thinking about how we can improve it further. Then we saw that even though we were able to having a laser that have a wide spectrum of wavelength to use, we were only able to transfer in the C band, which is the telecom band. So what was the limitation for that is basically like in the previous diagram I said, if I have to send a wider spectrum of laser lights, I need an amplifier that can amplify in all the spectrum. So that was a limitation that was there. So we were able to use only the C band, even though we had a quite S and L band around it. So it's basically a wide spectrum of information. We are able to use only a short region. So this is more like this is more because of the amplify issue, because the market available amplifiers works on mostly on C band and little bit of in L band. So this is more relatable to an highway you can think about. So in a highway you have 4 lines. You imagine in that way, and you are allowed only to use 2 lines of the highway. So it's just what will happen. The amount of traffic will increase and the amount of vehicles passes through will limit. So if you think about like, okay, if you're using the 4 lines in the highway, you can use the entire highway to make the vehicles move, and overall the amount of data transfer vehicles transferred will be passed will be really high. So this is the same way here. We have a fiber that can carry a lot of wavelengths or lot of bands, but we are using only C band because we have an amplifier that works only on C band. Now think about, we make an amplifier that works on S, C, and L band. Now you can use the entire fiber spectrum to work, like the fiber that can take a lot of informations through it. That makes the entire system efficient. So our goal was to make an amplification unit that can amplify in S, C, and L band. And how it is possible? It's mainly because the one of the best ways to do, according to us, was using a nonlinear frequency mixing, which is done by a device known as frequency converter. So this is the area we thought like we will work on and improve. So first of all, when I say about using a nonlinear frequency mixing, I will give a small idea about how the system looks like or how the phenomenon works. So this is a process known as cascaded different frequency generation, which we thought of like working on. So this, you can take this towards your electrical or electronics knowledge, where a signal mixing had been done to transfer information. So we have a pump signal that generates a second harmonic signal, and we have a signal which we actually has to transfer. So now this to the SHG signal as well as the uh, signal that we actually has to send will combine and produce an idler. So this is more like how in electronics people use frequency mixing. So this is a phenomenon we thought of like using, but to use it in photonics, we need an uh, more like an system that does a nonlinear process. And when I say nonlinear, particularly a Chi2 nonlinear process, Chi2 nonlinear process might be, it's very new for you, but this is basically a material dependent property that helps to do a frequency doubling. So about frequency doubling or second harmonic generation, I will explain little later, but this is just to give an idea. This is how a frequency mixing work. So when we think about doing a frequency mixing, it is mainly when I say a second harmonic generation or whatever it is, this is mainly a material dependent property. So all the materials can't give these properties. So there are very limited materials that can give it, and we need it in a thin film platform so that we can make it to integrate into a single chip. So we used lithium niobate on insulator platform, which is quite famous for this. This already have the property of electro-optic modulation, which is currently used in the conventional infrastructure of internet, where they use lithium niobate for electro-optic modulation. So it's already sorted out. So the other thing is, like as I said, we should have a Chi2 or a second order nonlinearity that we need to generate this frequency mixing. So this material have a good property towards making possible this second harmonic generation or this nonlinear mixing. So we had gone ahead with using this particular platform for our devices. And now we will get more about like, okay, have fixed a material platform that I should work with. And now we have to see how we can make this frequency converters or the device that can help us do this frequency mixing. So for that, I will give a slight intro about how a nonlinear mixing works and show a phenomenon basically known as second harmonic generation, how it works and so on. So if second harmonic generation works in this way, so you have a crystal or a nonlinear material, which is, this is designed to do a frequency conversion process. You send in a signal at a pump signal, say at 1550, and send it through a crystal, and it can generate, it can generate both pump as well as a frequency double wavelength along with it. So this is a property that particular materials have. So basically, if I send a red light through a material, it gives out a red light as well as a blue light. So it means when I send a one frequency in, I get two frequencies out. So this is what how a second harmonic generation works. And to see the quality of this process, it's mainly like how much good the conversion happens between this red light to a blue light matters. So that is how we quantify it. And when I say this, all these jargons, you may feel like, what is this? We have not seen something like this, but it's not the same way. We have used this almost in our day, like some part of our life. Say the pen pointers that we have used in our previous generation to use to show in our screens, like basic pointers that we have used. Those worked in the same technology as what I have mentioned now. So this is something we have used all through our life. Not all through our life, at least in the later part as a PhD student, we might have used this. So if I have to make this efficient frequency conversion, there are certain conditions that has to be achieved. So one is that a phase matching condition that has to be achieved. So this is again like when you send in a particular light through an nonlinear medium, it will generate a frequency double frequency only if both the light moves in the same speed. So think about a red light passing through an object and a blue light passing through an object. If you see in general, both travels at different speed. So this should not be this should not happen to get a frequency doubling in general, because basically this happens because when a light interacts with a medium, it creates an index which is related to a frequency it travels through. So it's more like you have to create a phase matching condition. Basically these two frequencies has to move in the same speed so that it transfers its energy. So if you see it in more like a signal kind of view, this purple line is the red wavelength or the red beam that goes into the crystal. And if the generating frequency double signal travels at the same speed of the send-in signal, it will the pump signal will transfer its energy to the second harmonic signal, and the second harmonic builds up. So this is a condition one has to achieve to get an efficient frequency conversion. And if this is not happening, basically the crystal will give you, if you send in a red light, you will just get a red light. You won't get any other frequencies with it. So this is one condition to achieve. And the other condition is basically known as modal overlap. So before saying what is modal overlap, I will give a short intro about what is a mode. So mode is basically how the electric field distribution of a light will look like when it passes through a medium. So we all see light passing through all the objects here, but when you see its field distribution in general, this have a pattern. So that distribution pattern is known as the mode, and this is uh, and a modal overlap is basically like when we generate two frequencies, how the frequencies overlap with each other in terms of the distribution. That is known as modal overlap. And yeah, everyone don't want to know all this. These are little deep into the technology I'm trying to explain. But yeah, this is basically the conditions one has to achieve to make an efficient frequency converter. So when I said about phase matching, there are different ways of achieving phase matching, but the predominant ways used in a chip scale technology is quasi phase matching and modal phase matching, which we use in our lab. So quasi phase matching is a technology where we invert the domains of a material and make both the red and blue light to travel at the same speed. So this is one of the mostly used technology, and this is very efficient way of doing it. And the modal overlap in this method is also really good. But some of the challenges of this technology is basically when I said I have to periodically invert the domains of the crystal. This is fabrication indensed way of doing this. So it's a fabrication indensed technology, as well as when you have to scale it up to a wafer scale or multiple wafers run. This is not quite repeatable, or you can't use the same parameters for different wafers. So basically, this is quite hard to achieve when you think about scaling up. So these are the kind of challenges this technology have, and many researchers are trying to solve this off. And one part of our lab, like my colleague named Aditya Dubey, is mainly working on this technology. So the other way of doing a frequency converter using a modal phase matching technique. Here, basically, you just want to make a structure or a waveguide, we say, and this can easily generate a second frequency doubling process too. So this is quite very easier way of in terms of fabrication. This is quite easy, but in terms of scalability also, it's quite good. But the only challenge here is like the overlap is quite bad. Basically, since I'm trying to engineer a geometry of a waveguide and try to send it through at equal two wavelength at equal speeds, I can't take a mode that is first order mode. So we have to use higher order modes to do this. So the overlap will be quite bad. And Again, these things are quite in depth of how the technology works. In surface, this is quite confusing. So sorry, I'm explaining this because I want to just make the technology to be more known to you. So I am trying to explain all these things. So we have to improve this overlap issue. So what we have done is basically we have taken particular modes that can give a good model overlap between the pump mode. So we have done that by using a vertical TE mode. Again, TE uh, modes and this is particular polarization which needs again a lot of time to discuss, so I'm keeping it short now. But this is particular polarization which people uses for particular technologies. That's it currently, I will say. If anyone have doubt, we can discuss more about it. So by using a particular vertical mode, we are able to do an good overlap, and we were able to achieve really good results with it. So we have designed these waveguides and we have go ahead with fabricating them. Again, fabricating this chip is very similar to how people do a microcontroller processors that we use in our laptop. The same kind of technology applies here, and we have used the same fabrication process to make it. So we have done it in RMIT and with some other collaborators who are distributed all around the world. So basically, we within RMIT we were able to fabricate these chips, and we have demonstrated that these devices can do a second harmonic generation in efficient way that we expected it to behave like. So we have demonstrated that okay, we can do this second harmonic generation very efficiently, and this means that now this chip or this device is capable of doing a nonlinear mixing, which I have started with to improve the internet. And when we compare these devices with the commercial devices, in general, commercial devices gives an efficiency of 60%, but and these commercial devices are quite big in size. These are not a chip technology; these are more like a bulk technology. So bulk chip technology. So what our devices are quite small in size, as well as it works 4 times better than what a commercial device works like. So all over, we were able to achieve a device or a frequency converter that we were looking for, and these devices are performing very good. And the results were like a 2 magnitudes better than what this current technology was done by others. So we are kind of leading in this technology, and this work had been published and presented in various places. So this work had been published in Laser and Photonic Reviews, which is kind of a popular journal in our field. And a review work about this whole scenarios had been accepted to publish in Optoelectronic Advances. And currently, we are more working towards how we can integrate this single frequency converter, a device, to an entire chip and test it in a real world. So we are working towards it, and it's almost in the wedge of doing a real world demonstration. So this is a part of my PhD work, and the essential output of this works will definitely help to build the internet of our infrastructure of the internet of our future, which will enable all the technologies that I have mentioned before. So I believe like I have taken little technical side about explaining it, but as a whole, if you take in a nutshell, it's basically we are using a chip technology to make our internet faster, and we improve individual components in this entire chip to make the internet transfer faster. So that is the whole picture of this research. But I explained mainly the technological stuff in the middle part of the slides, which might have made you confusing. So I would like to acknowledge my group, Integrated Photonics and Application Center, headed by Anand Mitchell, who had helped us to help me to do this research over here. And I would like to thank whoever had attended this meeting. And if someone would like to connect us to know more about our technology, you can use the QR link which is in the below. And if you want to speak more about integrating a chip or using a photonic integrated circuit in your experiments, you can connect me directly through LinkedIn with the QR code that is here. So thank you. So if you have any doubts, you can go ahead with asking it. Yeah, thank you.
Thank you so much, Jackson. So does anyone have any questions? Yay! I saw that clap. Is anyone open to questions?
Yeah, you can ask questions mainly about like how the system works or things which is quite common to anyone. But about the deep technologies, it might be quite confusing. I know it's quite boring, but I have to say, like explain those. I just explained them. Yeah.
Never call
Anyway,
your research boring. Regardless, I just wanted to let everyone know that this session has been recorded. And if you have any questions later on, please feel free to, Jackson, do you mind sending me your QR code for possible collaboration as well? So just send that over and I will broadcast it to everyone. Okay?
yep. Thank you, Cody.
If there are, if there are no
Yeah.
more questions, Jackson, do you want to say goodbye to everyone?
Yeah, goodbye to everyone. If anyone would like to contact me, you can contact, as Cody said. I will send my LinkedIn profile to you. Yeah.
All right, sweet. Thank you so much, everyone who came. Look out for my next email on the HDR seminar series. Okay, thank you.
Yeah, thank you. Bye-bye.
Thank you, Jackson. Thank you so much.
Yep.